Hello, welcome, and thank you for again joining us during your lunch break to zoom into the void with the Danville Science Center, presented by Danaki Associates. I'm Ben Wright, Immersive Experiences Coordinator at the Danville Science Center, and you are about to join me on a tour for the night sky for the month of September 2020. Today's virtual online interstellar discussion is simultaneously being broadcast through Zoom and to Facebook Live. And as always, you are invited to participate in that discussion. Those joining in Zoom can submit questions throughout our tour directly using the chat with host feature there in Zoom. And those of you joining via Facebook can submit your questions directly below this feed in Facebook itself. We begin today, as we always do, directly outside of the Digital Dome Theater in the backyard of the Danville Science Center. We can see that it is indeed set, if you look in the right corner, we can tell that it is indeed September 8th in the year 2020 CE, Common Era, or AD, Anno Domini, the year of our Lord, and it is just a couple moments past 12 p.m. We are facing the southern sky, and if we take a few steps back, we can tell that to our right is the west, and to our left is the east. Gazing upward, we can see that our central star, the sun, is still rising in the day. It has yet to reach its apex, the highest point in its apparent daily trajectory across the sky. We call that trajectory the ecliptic. In a little less than an hour, which we can jump ahead to, in fact, exactly at 12:59 p.m. and 2 seconds, the sun will reach its apex, officially marking solar noon, after which the sun will begin descending until it sits in the west, marking the beginning of nighttime. This path, the ecliptic, is actually not the same each day. It changes throughout the year. The sun reached its highest point, made its highest annual journey across the sky back on June 20th with the beginning of the summer solstice. Since then, the ecliptic has been sinking lower and lower in the sky until it reaches its lowest point for the year on December 21st with the beginning of the winter solstice. On the 22nd of this month, the sun will reach one of its two halfway points between these extremes when we welcome autumn with the autumnal equinox. The start of fall, like the start of all our seasons, is due to planetary tilt. Our planet does not sit perfectly upright on its poles, but rather is tilted at 23.5 degrees on its axis. This tilt results in different parts of our planet receiving different amounts of direct sunlight throughout the year. During the summer months, the northern hemisphere experiences more direct sunlight and warmer, longer days. In December, January, and February, the northern hemisphere receives less direct sunlight and thus colder and shorter days and longer nights. On September 22nd, which we can use stellarium to jump to the 22nd, moving forward 15, 17, 18, 22nd, at approximately 9:30 a.m., the ecliptic, the apparent path of the sun, will cross directly across, we'll get rid of the Science Center to give us a better view, will cross the celestial equator, that imaginary line that separates our planet in half. When those two lines cross, that marks the official start of astronomical fall. Tracking the seasons is one way humans keep track of time. We've been observing and tracking time since the very beginning. The earliest humans observed the changing lengths of shadows throughout the day. They would organize events around these different lengths using tools ranging from knots and rope and cuts and sticks to towering stone structures called obelisks and smaller, more accessible sundials. Shadows are their shortest at noon when the sun is roughly overhead. Post-meridian, afternoon, shadows lengthen until full night arrives. Following sunrise, they continue to shorten. This is why we separate each 12-hour day into AM and PM. The point at which the sun appears directly overhead varies with location. That's why we experience different time zones. When the sun is overhead in California, it's 3 p.m. in Virginia. That's why we calculate the two locations as having a 3-hour time difference. Two 12-hour periods of time make up a 24-hour day. But why 24 hours in a day when minutes and seconds are grouped in orders of 60? Ancient Arabic navigators measured the height of the sun in the sky by holding their hand outstretched in front of their faces, marking off the number of spans. An outstretched hand subtends an angle of about 15 degrees at eye level, with a full circle being composed of 360 degrees. 360 divided by 15 equals 24 units, or 24 hours. Further, the number 12 and its multiples held mystical significance to Babylonians living over 4,000 years ago. Their astronomers broke the 360 degrees in a circle each into 60 subdivisions, 60 being a multiple of 12 and 5. They did the same with the 24 hours that make up a day, thus 60 minutes in an hour and 60 seconds in a minute. The ancient Egyptians created the first calendars based upon the cycle of the moon. It takes a little over 29 days for our moon to go through all 8 of its phases, thus producing a month of roughly 30 days. This occurs 12 times throughout the time it takes the Earth to make one trip around the sun, thus 12 months in a year. 12 times 30 equals 360. The ancient Egyptians added 5 additional holy days to the year for the worship of their gods Osiris, Horus, Set, Isis, and Nephthys. On these days, no work was to be done, thus making a calendar year 365 days. A calendar, however, is a tool used by humans. Humans like regularity. Unfortunately, planets don't. The Earth's orbit is elliptical rather than circular. Things like interstellar gravity result in some days actually being longer or shorter than others. Following a strict guide of 365 days in a year results in the seasons occurring at gradually different times from year to year, about 1 day off every 4 years. In 46 BCE, Roman Emperor Julius Caesar added an extra day to the calendar every 4 years to account for this shift in the time of seasons. 1,600 years later, the administration of Pope Gregory XIII further stated that years ending in 00 should not include a leap day unless also divisible by 400, bringing us to the Gregorian calendar that most of the world follows to this day. Having time line up with the seasons was and is vital for agriculture and commerce. Seasons occur in locations where Earthlings aren't even present to record them. Seasons on Earth are the result of our planet's tilt. The other planets in our system also have various tilts on their axes. Mars has a similar tilt to Earth's at 25.2 degrees. Its seasons are similar in duration and nature to our own. In comparison, Uranus is almost completely tilted on its side at 97.8 degrees. We don't even know if Uranus has seasons, and if it does, what they are like. The furthest planet from the sun, Neptune, is currently experiencing summer in its southern hemisphere. A summer, however, that lasts for over 40 Earth years. Neptune has a similar, though slightly greater tilt on its axis to Earth at 28.3 degrees. Being much further away from the sun, Neptune's revolution is much longer than Earth's, clocking in at 165 Earth years. 165 divided by 4 seasons results in 41.25 years of summer, fall, winter, and spring, each on the icy blue planet. Neptune is 30 times further from the sun than is the Earth. This results in the planet receiving 1/900th the intensity of sun exposure that we do here, making it a very cold place indeed. Temperatures average negative 350 degrees Fahrenheit on Neptune. Its core, however, is as hot as the surface of the sun. This heat differential results in Neptune being an incredibly windy planet, with wind speeds exceeding 1,200 miles per hour. Neptune's rich blue color is the result of trace amounts of methane in its atmosphere. Methane absorbs the color red and reflects the color blue. Like our blue planet, Neptune does possess water, though most of it is frozen. Only one spacecraft has ever visited Neptune, Voyager 2. Launched in 1977, it took the craft 12 years to reach the ice giant. At 2.8 billion miles from Earth, Neptune is the only planet that cannot be seen without the aid of a telescope. The planet reaches opposition this Friday, the point at which it is opposite the Sun from Earth. This will present Neptune at maximum illumination from our point of view, making it an ideal time to attempt a glimpse. A spacecraft will be launching from the Commonwealth on the 30th of this month. Northrop Grumman's Cygnus NG-14 will launch from Wallops Island Flight Facility in Virginia, just south of Chincoteague, on a resupply mission to the International Space Station. One of only two companies, the other being SpaceX, to be part of NASA's Commercial Resupply Services program, this will be the 14th flight of the robotic cargo spacecraft, its 13th to the ISS. During its tenure, Cygnus has delivered the largest payload ever to the space station at 7,700 pounds, launched a series of cube satellites, and during dock acted as an extension to the ISS with experiments being conducted inside Cygnus. Its next milestone is the planned launch of the habitual logistics outpost HALO. HALO will serve as an outpost for NASA's Lunar Gateway, allowing for close, safe exploration of the lunar surface. The International Space Station has made its own headlines as of recent. For over a year, the ISS has slowly been leaking air into space. The rate of the leak has increased, and last month NASA announced that the three people currently on board the ISS, American Chris Cassidy, and Russian cosmonauts Anatoly Ivanishin and Ivan Wagner, are engaging in procedures to isolate and locate the air leak. The ISS is always leaking a small bit of air, but this is usually resupplied during cargo missions like Cygnus. However, such resupply missions may not occur quickly enough should this current leak become major. In a true emergency, the three crew members could return to Earth on the Suez MS-16 spaceship currently docked to the station. The crew is currently collectively isolating in an attempt to determine which module is responsible for the leak. Whether you're isolating in space or here on Earth, we do not want you to feel alone. We come now to the point in our presentation where we turn over to you for some of your questions. Again, if you are joining us via Zoom, you can submit your questions using the chat with host feature within the program. And if you are joining us via Facebook, then you can submit your questions directly below this feed, and I will attempt to answer them. Our first question comes from Hannah. Hannah asks, what is the celestial equator? Is it different than Earth's equator? Good question. The equator is an imaginary line. It's not actually there, but it's what we use in maps to help us get an idea of the two different halves of the Earth, the two different hemispheres. The celestial equator is just if we took that imaginary line and extended it into space. During fall and spring, for those individuals living along the equator, they will experience almost directly 12 hours of sunlight and 12 hours of day. That's because the sun passes over the equator. For us in the northern hemisphere, the sun passes almost directly above what's called the Tropic of Cancer for the summer solstice, and then for the winter solstice, it passes over the Tropic of Capricorn. Of course, that is opposite for folks in the southern hemisphere. They experience the reverse seasons on those dates. But those lines and the way they intersect with the path of the sun with the ecliptic is how we know when our seasons will occur. Good question, Anna. Next question from Alice, also having to do with seasons. She asks, why do planets have different tilts? Did they get knocked out of place? Well, kind of. Possibly. When the planets were forming billions of years ago and gaining their different masses, it's possible that they did indeed collide with each other when they were still small, what were known as planetesimals. When the larger mass planets like Jupiter would collide with the others, it would have an impact on them. This is the idea for most of the planet tilt, with the exception of Uranus. Uranus has that weird over 90-degree tilt. It's possible that an asteroid or another space object collided with Uranus at one point in its history. We're not completely sure why. That has a lot to do with it. Even further in that range is that the Earth's tilt, most planets tilt where they point. Their axis also changes due to the composition of our core. We talked during our last void that Earth's North Star Polaris is the point where our axis points, but that hasn't always been the case. The North Star used to be one called Thuban, and eventually the North Star will change from Polaris to Vega. About every 13,000 years ago or so, our axis points at a different star. This has to do with our core, and the best analogy with that is think about an egg. If you spin an egg, it doesn't spin completely perfectly, but wobbles because the yolk and the white are different densities. While our planet has a solid core, it's surrounded by molten liquid. That means as we're spinning, we wobble a little bit. And that wobble eventually changes our alignment. Not so much to say correct our tilt, but it can alter where our tilt is exactly pointing, where our axis is pointing. So, I hope that answered your question, Alice. I apologize, Alice. Another question from Malcolm. Malcolm asks, why are some months 30 days, 31 days, and February has 28 days? The naming of our months has to do a little less with space and a little more to do with culture. Many of our months are named for different Greek, Roman, Norse gods. Same thing with our days of weeks. Many people think about Thursday as Thor's day, Thor being the Norse god of thunder, but also Freya is Freya's day, another Norse goddess. Many of our naming of our days of weeks and our months is due culture. And our overall calendars tend to be a combination of our understanding of the empirical sciences, those things we can see like planets and stars, and those things that maybe we can't see with our eyes or hear with our ears. Even with the Egyptians, when they added those days to the calendar for those gods, the Gregorian calendar is not absent from us using those names of religious holidays and observances. We incorporate those often into the ways that we observe and measure time. Specifically, so why does February have 28 days as opposed to 30? Don't really know. It's the way we organize the calendar under that administration of Gregory the 13th to incorporate all 365.24 days of our year. Jacob asks, will brooms be able to stand up by themselves on the fall solstice? If so, how? Good question, Jacob. Unfortunately, not really. At least not more than they normally would. During the fall equinox and the spring equinox, there is a bit of an internet rumor going around that there'll be more of a gravitational pull on the Earth during those times. The fact of the matter is the amount of gravitational pull on our planet varies constantly due to the position of things like the moon, the sun, and other planets. The arrangement on those days isn't such that perhaps brooms would do something different. If you saw a video on TikTok or online of that happening, fact of the matter is brooms have a pretty solid or low center of gravity, and their bristles are kind of easy to spread out. So with a little bit of practice, I bet you can get a broom to stand up on its end today, tomorrow, and on the 22nd. So it's a pretty neat trick, but it's maybe not as impactful as we'd like to believe. And one more question today. Zach asks, when Voyager 2 launched, was there any need for correction along the way? And if so, how? Yeah, Voyager, again, took 12 years to reach its destination. And yes, it did need some correction. In 1981, actually just about halfway through its journey, when it was passing between Jupiter and Saturn, it was believed that Voyager would maybe miss its mark on its way to Neptune. It is a bit of a misconception to think that once spacecraft enter space, that they're just sort of firing their rockets and going. Really, once they get up into space in areas where gravity has a little bit more impact or a different impact than here on Earth, and there are different resistance to wind, once they get launching, most spacecraft can kind of just go, orbit, and continue along their trajectory. If they If for some reason they don't follow that trajectory, then yes, these spacecraft can fire boosters or rockets to get back on path. And that's exactly what happened with Voyager 2. Signals, radio signals, think not radically different than the signals you may get in your car, AM and FM, but a little different, were sent to Voyager to launch its booster rockets to get it back on track in enough time that it was able to make its trajectory past Neptune. Voyager now has exceeded past Neptune, has actually left our solar system, moving into interstellar space and continuing its journey. We are glad that you've joined us today on our journey through space. We hope that you will join us next month for October's virtual online interstellar discussion taking place the second Tuesday in October. That is the October 13th, the day after Columbus/Indigenous Peoples Day. We'll be joining you again via Zoom and through Facebook Live. In October, again brought to you by Danaki Associates, we will be discussing the blue moon for October 31st, a pretty rare occurrence, and diving deeper into our red planet, Mars. We hope to see you then. Until, stay safe, stay healthy, and as always, stay curious. Thank you, and have a wonderful day. Bye.